Welcome to another video explaining the universe using the particle model. But first, a comment about our book. David and I are still working on our book, Principia Mathematica 2. This is the icon of the book, and we look forward to getting it done and having it out to our viewers. Well, today's video is about the N2 particle which I have virtually given it no respect at all. It's the G1, G2, and then the N1. These three particles get all the respect, but the N2 is hardly ever mentioned. But it was clear at the start that if the G2 particle was the particle that bent light, it had to be faster than light. It's something that modern science today just seems to miss. It just completely ignores the idea. But where does this particle come from? Subatomic atoms. A subatomic atom with a nucleus and an orbital was the logical way for the TPM model, at least, a logical way for nature to have a particle faster than light. And yes, modern science refuses to admit there's a subatomic atom. They only talk about subatomic particles. But there can be no bending of light in a gravitational sense unless this lower level atom exists. To bend light, the G2 must be faster than light, it must be a real particle, and it must be able to pass through the object that it's moving. So what does a subatomic atom look like? Well, I don't know, and David, he says he doesn't know either, but I tend to use the Bohr model because it's simple, people are familiar with it, but there's no guarantee that it looks like the Bohr model. And in our book, David has a graphic of an atom in molecules. They're based on the model that develops from the Schroeder equation. That may not be right either. But you know, when you start to talk about atoms, you want to have something you can visualize, but admit that we don't know. Now, level 1 atoms have a nucleus like the N1, we call it the nucleon, and an orbital, the G1, which is like the electron. So it was logical to suggest that the subatomic atom has a level 2 nucleon, N2, with an orbital, G2. If the level 2 atom has a nucleon and an orbital, it must be smaller than the level 1 atom, so the G2 is much faster than the speed of the G1. Hence, this is just a physical property. It gets smaller and smaller. It has to go faster if it's going to stay in orbit. If the G2 is in orbital, it has to move fast enough to move around a very small nucleus. Well, here was my problem recently. Dave and I were talking about double slit, and I actually got some of my drawings wrong, and he pointed that out, and so we're straightening that out in our book. And through that discussion, I recently discovered that the G2 mass of an object is not just based on G1 density. I'd been saying that over and over and over again, even though I've admitted there could be more to it, because I really didn't understand too much. I just got this impression from how I saw light bending and magnetic fields bending and so on. So I stayed with it because it generally works. But it was clear when in understanding the double slit, that I needed to pay attention to the N2 particle. Now this has to do with what we generally call mass, and people have different kinds of different definitions. But this is a very general definition for mass that I think applies at all levels of the TPM model. Mass is a property assigned to an object to help describe its motion. Newton was the one who did that in the first place. He was looking at the interaction of two particles, and he said if he could assign a value of mass to each particle, he could then describe what happened when they both hit. And he ends up with force equals m times mass times acceleration. But that's a general description of what mass is, but what's really going on? Well, here, level 1 objects. That's level 1 atoms like hydrogen, copper, iron. These objects move when a G1 hits the N1 nucleus or the G1 orbital of the atom. G1 can actually pass through an atom. It's a very small, it's a tiny particle that it can pass through the open space of an atom, but when it hits the N1 nucleus or the G1 orbital, it pushes it, it moves it. Same for level 2. Level 2 objects move when the G2 hits the N2 nucleus or the G2 orbital of the subatomic atom. We call this G1 mass. When G1 causes the motion, G1 mass is the value we assign to objects to help describe that motion. Same with G2 mass. Okay, so this is G2 particles that bend G1 light. This is a drawing I made a long time ago where this is when I made this drawing the very first time, although it was a pencil sketch on paper. This is when I came up with the idea that there was another force faster than light that was bending this light. The red laser light is made up of streams of G1 particles, lots of this high intensity light, all with a repetitive pattern that matches the red light, like 700 nanometers. Most of the G1s pass through it. They pass straight through and out, pass straight through the glass. The G1 has open space because it's made of lower level atoms, subatomic atoms. It has lots of, the particle itself has lots of open space because it's made up of, that's how it gets that open space. If it didn't have the open space, it wouldn't bend. Some G2s will hit and push the G1s. They hit and push the G1s by doing what? Hitting the N2 or G2 particles, because that's the only, they don't collide with the G2 or the G1 or the N1 particularly. They collide and hit the N2 of the and G2 of the G1 particle, the subatomic atom in the G1 particle. Sometimes this gets a little tricky saying this. G1s move when G2 particles hit the N2 or G2. And it turns out that the prism has both G1 mass and G2 mass. You can take this prism, put it on a scale, and weigh it in grams or pounds, and you'll know how much it weighs. That's its value of mass. But it also has G2, it has a G2 mass because light bends. And what we're saying in the particle model, there's a G1 particle field surrounding this. There's a G2 particle field surrounding this in all three dimensions. And it's the G1 particle with its net force that allows us to weigh the prism in forms of G1 mass, kilograms. Don't think you can weigh. I'll get into that in a bit. Well, here's a much more detailed, I'm trying to emphasize this point about the F2, the net force on the G1 particle as it approaches. You can think of this G1 particle as an apple. It's red. Someone throws the apple and it's falling to the ground. And it has a G1 mass. The apple has a G1 mass, and the Earth has a G1 mass, and you end up with a F1 force pushing the apple down to the Earth. That force is based on Newton's equation. Well, at level 2, we have a similar situation. Here we have a G1 particle that's coming at the prism at an angle, and there's an F2, net F2 force generated from the G2 particle field around it that pushes on the G1 particle and moves and bends it as it enters the prism. But it doesn't literally push on G1. What the G2 particle does is it pushes on the subatomic atom. Here's a subatomic atom with an N2 nucleus and a G2 orbital. Here's a level 1 atom. The glass, the prism, is made out of these atoms, but inside the G1 and the N1, the G1 has a huge number of N2 particles and G2 particles, and the N2 particle is bigger than the G2. So it's going to hit it more often. It becomes a major part of the G2 mass of the prism. In the particle model, there is an empirical equation you can use for calculate the force on this particle. It's the product of the mass, G2 mass of the prism times the G2 mass of the G1 divided by the distance between the center of the G1 and the center of the prism. And that's the product of that is the force is proportional to that product divided by r squared. It has a gravitational constant, but it's not G1. It's not the universal gravitational constant of Newton's equation, but it has its own. We don't know anything how to handle this equation yet. We don't know how to define the mass, G2 mass. We don't know how to name the force, and consequently, we haven't done experiments that'll get us the value this gravitational constant level 2. But it is identical, almost identical to Coulomb's equation. The electrostatic force between the proton and the electron divided by the distance between has a constant K, and that's the electrostatic force between the proton and the neutron. It's exactly what's happening in the TPM model. But this force, although it hits the G1 and pushes it, but it's not really, it's when you get inside, it's really hitting the N2, and there's many, many, many more N2s in here than there are N1s or G1s. So the N2 becomes a dominant factor in the G2 mass of any object. Well, going to go off in another direction here, but this is measuring the mass of the electron. If you haven't watched these two videos, this is very interesting. I made both of these maybe end of last year and the earlier this year. Really some interesting analysis of how this experiment with this apparatus works. I recommend you watch it. I'm going to talk a little bit about it here. This is the apparatus. It has 2 Helmholtz coils, and it's got an electron gun, which is not shown in this picture, and they generate an electron stream, and they can control the stream and get it to move in a circle by adjusting the current through the coils and adjusting the voltage on the gun. And if you watch those 2 videos, you'll see this lady in this really old video explaining all the equations and how they get the mass of the electron by measuring the diameter or radius of this circle. Interesting how they do that. The interaction, okay, the Helmholtz coils provide a magnetic field. You can see it there. The electron gun is controlled by a power supply, uses an EMF voltage to generate a stream of electrons. That stream in turn develops a secondary magnetic field around the stream of electrons, using their terms, electron. And it's the interaction of these two magnetic fields that sets up a G2 gravitational field, causing the electrons to move in the circle. G2 particles bend this stream of electrons, bending electrons. And so you're measuring G2 mass using magnetic fields and electric fields, and all of that is based on G2 mass. They're actually measuring it correctly. It's quite amazing. Unfortunately, in the videos, I point out the fact that they explain it in terms of kilograms. The mass of the electron is in kilograms. I prefer this one because this expression for mass, 500,000 electron volts per c squared, is more related to how they're measuring it than kilograms. They're not weighing the electron using a scale that uses G1 particles. That's not the way they're doing it. They're doing it with G2 gravity, even though they don't say it that way. Okay, measuring mass. The prism has G1 mass and G2 mass. I said that earlier. The G1 mass of the prism can be measured on a standard scale, which we would call a G1 scale. Well, there is no scale to measure G2 mass of the prism. You can't put it on a scale. See, here's just a picture of a scale. And what are we really measuring here? This gets to a key question here. What are we really measuring when we measure the prism using standard weights on a scale? G2 forces all the way around, and I'm just highlighting the two net forces, F1 and F2, that are imposed on here. F1 is there. We all understand that. What we don't talk about is the fact that F2 is there. You can't get rid of it. It's there. You think you're doing G1 gravity, but you're doing G1 and G2 gravity because they're both there. You can't separate it. How about a G2 scale? Could we build one of these? Yeah, this is the same drawing, because why? You can't get rid of G1s or the net force of G1 gravity. They're both there, but could we build one, and could we somehow with this needle tell us what the G2 mass is? Well, my first impression is, well, you got to build this out of you got to build a scale out of G2 atoms, level 2 atoms. That's not likely to happen. So my initial answer is no, you can't build an instrument to measure the mass of the electron. But we just did that. I just showed that. With this picture. This instrument is made out of level 1 atoms, and it's measuring the mass of the electrons, and it gets a value for the G2 mass. They say kilograms, I say million electron volts per c squared. But nonetheless, well, where is the G1 gravity here? Well, actually, it's holding the apparatus down. By the way, I looked for a name for this. The only one I could find was this. If you want to buy one, you want to buy a E over M apparatus. That's electron charge over mass. This is the electron mass ratio that they can measure with this instrument, so they call it an E over M apparatus. But the G1 gravity here is negated because there's no part of G1 gravity that affects this measurement, except one. There is one part, the G1 particles surrounding this, hitting this circular beam of G1 particles, say it in terms of the particle model, will collide with it and knock out. It'll knock out electrons out of this stream. Well, it turns out the electron gun continuously generates new streams, so it doesn't really matter. You lose some intensity temporarily and it doesn't matter. G1 gravity is negated here. The instrument is made out of level 1 atoms, and we're measuring G2 mass of the electron without using where G1 gravity is negated. It has no effect. Here's a whole new thing, man. Maybe one day I'm going to be able to take the time to explain the Penning trap. Let me read this. It's from this link. I apologize for that smallness of that, but I will put it in the description of this video when it's released. Let me just read this. Penning traps are well proven as suitable scales. This is a scale like a chemistry scale in a chem lab. It's a scale for ions. In such a trap, where's my mouse? In such a trap, it is possible to confine nearly indefinitely single charged particles, such as a proton, by means of electric and magnetic fields. They're doing it using G2 gravity. Here again, the G1 gravity is negated in this instrument. The instrument's made out of level 1 particles, and it's measuring G2 gravity and is built in such a way as to ignore G1 gravity. Inside the trap particle performs a characteristic. I like it, performs. The particle doesn't perform anything. The particle is controlled by and moves, controlled by the electric and magnetic field, but the trap particle performs a characteristic periodic motion at a certain oscillation frequency. This frequency can be measured, and the mass of the particle calculated from it. The mass of the ion. These are for ions, charged particles. They claim, if I were to explain this in detail, I would have to be able to explain that oscillation, whether it's a positive ion or negative ion. It should work the same way. In order to reach the target high precision, an elaborate measurement technique was required. No explanation here. I don't apologize for that. That's a lot of work that I have to do to analyze what's going on. That takes time. I just wanted to point out that you can not only measure the mass of the electron, the G2 mass of electron, but you can do it for ions, and they do it in what's called a Penning trap. Well, this is a neat video. I looked at 3 different videos, and when I saw this one, I said, yeah, I got to tell my viewers about this one. It's a great video. Here's the link. This is the Penning trap. This is a mechanical analogy, if you will, but a physical working one. This particular snapshot is taken about not quite halfway through, and this lady who's giving the talk has this spinning around. It's not moving real fast because this is a big ball that has some mass. This is G1 mass. And as you spin this around, it traps it, so it's like holding it in a cup. But there's no cup. There's just this spinning saddle. I call this a saddle. This picture here, and when it gets to a point where it actually tends to move back and forth, you can actually see it a little bit. Later in the video, this is quite almost 3/4 in, she has the actual instrument on, the light's out, a red light shining on the particles. What she did was she took pollen of some sort, rubbed the pollen on her pants, on her leg there, where she was wearing some pants on her. Yeah, and charged it, electrostatically charged all these particles. Then she inserted them somehow into this Penning trap, and you can watch the video. You can see these moves. The motion, for the most part, seems to be up and down. Don't know if that's the only way, if that's the way it's supposed to be moving or not, but that's what I saw. But it's interesting. You can watch it, and she slowly takes the pollen out, and you can see fewer and fewer of them, hopefully, to see how they're moving. Neat demonstration, both showing a mechanical version. Here, it's you gotta love it. Ian L. Deneau for magnetic field actually shows how spinning drums look like two magnets. Here you've got a spinning saddle that cradles this ball in this one spot, vibrating back and forth, and these vibrating up and down or back and forth. Great video. Suggest you watch it. Okay, in summary, the standard scale for measuring mass in kilogram not only measures G1 mass, but includes the effect of all lower interactions. I said in the video earlier, it included G2. Well, you can't get rid of G3 and G4 if they really exist. They're all there. If it's infinitely down, however you like to think of it, down all the way to infinity, they're all there. When you measure G1 mass, you're measuring the effect of all those interactions. Not just the G1, but the G2 and on down. There is no mass included when you measure the electron in the E over M apparatus. Went through that. There is no, this is amazing to me, that you can build an instrument out of level 1 atoms, exclude level 1 gravity, and get strictly the G2 mass of the electron or the ions. One in the apparatus here and one in the Penning trap. TPM indicates, of course, I'll repeat it again, that N1 and G1 should not be stated in terms of grams. That may be wrong eventually. There may be a correlation that can be made between them that is not just between equations, but to me at this point, since you're measuring it using an electric and magnetic field, which generates a G2 force field inside, causing these things to either the electron to bend in a circle or the ion to move back and forth in the Penning trap. It's not G1 gravity, it's G2 gravity. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.